Wait, so for lab, we just do the purpose and then we jump right into the procedure. Don't have to do, well, and equations. We don't
I have to read it again. I don't know. Okay, I am going to actually start reviewing for the exam that is 1 week from today. So you get more review time. Oh yeah, look at that. So let's review what we have done in this class so far. We have done, what's the name of this equation here?
That is,
Whoops, too much. This equation here.
that is the equation for Coulomb's law.
Righto, dumpardo. That's Coulomb's law. KQ dQ over R squared is dF. Now, I did not write this as a vector equation. It is a vector equation. There's a direction to the force. But remember, when we use this equation, just like, like everything we did yesterday, what's the difference in that and the equation that follows it?
The equation that follows it, there's no dq.
No,
there's no q.
There's no q. I divide out the q because electric field is the force per charge. So the two are fundamentally the same equation, just with that definition of what electric field is. So in the problems you did yesterday, you were doing electric field, so it was the right half.
Right.
And we did the magnitude, and then we applied the direction after we had found the magnitude. We didn't integrate until after we had the directions. We integrated each direction then separately.
Really quick, k is equal to 1 over 4 pi epsilon 0.
Right. So I just wrote it both ways, just to get the k in and out.
Okay.
So we used this, and we found the magnitude, then we broke it into components. Remember, it had all of those questions for you to answer, and it was asking you to break it into components, making sure that you have that thought process going on. And then we integrated each component separately. Now the second equation, what's the second one there?
Gauss's law.
Gauss's law. What does Gauss's law tell you? What fundamentally is Gauss's law saying?
The flux inside a Gaussian surface is what's, no, that's not right. That's part of it. That's not right.
So state how you think is right.
It's finding the electric charge in relation to the Gaussian surface. I think that's right.
In a nutshell, it says that the electric field coming out of a surface, a closed surface, is proportional to the charge enclosed.
Okay.
Right, so the electric field, we talk about the flux, and the flux is integrating the electric field through a closed surface so we know how much is coming out of that surface. I know I'm standing right beside you just yelling into your ear.
Yes.
So it's that relationship between the electric field and charge. And the more I teach, the more simple this seems. It seems to simplify everything in my head, but I can tell you that it didn't seem to simplify anything in my head when I was in college.
Right.
So you've been using that, and in what situations, both of these allow you to find the electric field based on charge. Which one, or how do you choose which one to use?
One of them is if you're trying to find it through a surface, like you have a sphere. No, that's not quite right.
Let's just say I'm trying to find the electric field at this location.
I'll then use
It's not always use the first one or always use the second one.
no.
It's based on fundamentally which one's going to be easier. And we determine which one's going to be easier by looking at, is there an exploitable symmetry? There's an exploitable symmetry, that is, if E dot dA, for instance, is 0 on this surface and parallel on this surface with, electric field either constant or easy to integrate, then Gauss's law. The key situations we've done, We've exclusively done electric field is perpendicular to dA, or electric field is parallel to dA, and electric field is constant on the surface. So we restricted ourselves to symmetries that we can do the calculus without actually doing the math, just by making logic arguments. If you don't have that kind of symmetry, it's probably going to be easier than to use Coulomb's law. And remember, we did like a wire, the electric field caused by a wire with a continuous charge distribution. We did it with both methods. And I think you would agree it was easier doing the wire with Gauss's law because it had the exploitable symmetry. But if we'd have a curvy wire, well, that wouldn't have worked for us. Now, we didn't do a curvy wire. Oh, well, we did a circular wire. That was like the first problem I did. A wire that's in a circle. Because then it doesn't have a nice exploitable symmetry for Gauss's law, but the symmetry does work pretty easily for Coulomb's law there. What's the third equation?
Third equation is the differential form of Gauss's law.
Okay, so these two here are both Gauss's law. I still can't decide if it should be SS apostrophe S or just SS apostrophe. I was taught SS apostrophe, but I read something recently that suggested SS apostrophe S would be correct. Book authors can't decide either.
No.
So those are both Gauss's law. So how do we go from one to the other? It has to be a mathematical pathway between them, right? If they're both Gauss's law.
Right. I guess it's the integral of dA is equal to the part. Is that the partial derivative? No, that's not.
Well, let's think about what is charge. How did you calculate charge in your problems yesterday?
We got charge by looking at the Q enclosed is equal to the volume.
I really not sure.
Rho dV.
The charge was the integral of the charge distribution, dV. And so if you look at those equations, you have an integral of E dot dA on one side, integral of rho dV on the other side. Fundamental theorem of calculus is the derivative of the integral gives you the argument of the integral.
Right.
It's a little different here because this is vector calculus, right? Integral of E dot dA. It's not just integral of E dA. So it's a little different, but that's effectively what we're doing. We're just taking the derivative of the left side, the derivative of the right side, and we get this equation. Now, like I said, it's a little different, but that's the idea. Here I just went through, we've already talked about this, just so it's in writing, you can look at it, how you decide if you're going to use Coulomb's law or Gauss's law. If you have a nice spherical symmetry, cylindrical symmetry, or the planar symmetry, which you did all of those in your homework, those are the cases where you're definitely going to use Gauss's law. If you don't, you're likely to use Coulomb's law. And I've talked about that stuff. Just a reminder that charge can be distributed one-dimensionally, two-dimensionally, or three-dimensionally. When we did a wire, that was a one-dimensional. That was why you had the question. Well, how is the charge distributed? Is it linear, aerial, or volumetric? And so if it's on a wire, linear. Mm-hmm. If it's on a sheet, like let's say I have a piece of aluminum foil that has charge on it, then it would be aerial because it has, negligible thickness. And if it's on something that is not negligible in thickness,
that's the
volume. So you have to use the right one for your work. You could always go to the volumetric one and just say, well, this dimension is approximately 0 and get to the others. But why do extra work? And remember the words that we said here. Use geometry to break into components. So I did the magnitude, then I used my knowledge about, electric field goes out of positive into negative to determine directions, break into components, and then do each component independently. If you don't do that, you're going to end up in a world of hurt most likely. I'm sure there's a case where, oh, it's easier this way, but generally speaking, you want to do that. Notice my last statement. Gauss's law can be used outside of these symmetry conditions, but it is often very difficult.
And that's when we use Coulomb's.
Yeah. And if it's not very difficult, well, great. So applying Gauss's law, identify your Gaussian surface. I don't think you've had any question about this.
No.
But a lot of students have, and I have, and that's what is the Gaussian surface.
That's just a surface that you create either inside or outside.
It's an imaginary surface. It's
Imaginary
not a real one, because people are always looking like, well, it's a sphere, so it's the surface of the sphere. No, it's when you make up with the ranges you want for your problem.
And it could be either inside or outside depending on requirements.
Yeah, depending on where you want to find the electric field. So that's an important thing just to understand what the Gaussian surface is. You make it up to match your symmetry to make it easy. Calculate the charge enclosed by the Gaussian surface. So you do this. These are two independent calculations. You can do one first or two first. They're independent calculations. And then you set them equal. That's the key for Gauss's law. You do equation left side, equation right side, you set them equal, and then you solve for something.
So the charge equals the flux and solve for.
Well, charge enclosed over epsilon zero. You kept forgetting over epsilon zero yesterday.
Oh, yes.
So if it asks what the flux is, you're supposed to, not highlighter anymore. If it asks what the flux is, you're supposed to calculate this. You don't say, aha, well, I know the flux is equal to charge enclosed over epsilon zero. Yes, that is ever so true. But when it asks what the flux is, it's asking for that side so you can put them together.
So then you can solve for E.
Yeah. Or
In most cases.
yeah, in most cases. I say we did the case like with a conductor, and we know the electric field inside the conductor is zero, and we could solve for how much charge is enclosed. Differential form. Yeah, just going to move on from that. Here's something that we've covered, at least the top one. The bottom one, maybe not, but the relationship between the top equation and the bottom equation is the same as our relationship with the differential and the integral forms of Gauss's law. So the upper one is actually the definition of electric potential. The electric potential difference is defined as the change in potential energy per unit charge. Right? That's definitional. That's how we define electric potential.
Delta V is volts.
V is electric potential, which has units of volts, and thus we colloquially call it the voltage. So I'm saying electric potential because that's the true term. Voltage is what we always think.
And Q is just Q, not Q enclosed or anything.
Right. Because the potential energy is not held by a single charge, it's held between the charges.
Mm-hmm. And W is work.
W is work.
Okay.
So change potential energy is defined as minus work. That's again the definition of potential energy is change potential energy is minus work.
Force times change of direction. Yep, that's right.
So integral force dot dx, not change. Well, not
Well, dx is changing.
it is. It's changing. It's distance, but it's a vector. So I'm
Okay. And then I don't get how you go from force to QE.
That's again a definition.
That's a definition.
The definition of the electric field is the force per unit charge. So that means force is electric field times charge.
Yep.
So everything is just definitions going across, plugging in one definition after another. Well, except for the last line, because the last line I canceled the Q's.
Yep.
That's the only thing that wasn't a definition on that line.
Mm-hmm.
So the voltage difference is minus integral E dot dx. And you do that along a path. So it's a path integral. Path integrals can be hard or easy. Because it's a dot product, you can choose any path you want. It's not going to matter because electric field is a conservative force. So choose directions where E is perpendicular to dx on part and parallel to dx in the other part to make your life easy. Now, if we were to take this and take the derivative of both sides, now, I do have to point out something. The definition is change in voltage.
Yes.
We set a reference point. When we do this whole calculation, at the end we set a reference point. So we can say voltage, if the voltage change is this, then the voltage at this point is equal to the voltage change between this reference point and here. So I can say V is equal to V0 plus delta V. So given that, then if we take the derivative of both sides, and notice, what is that? Do you know what the name of that upside down triangle is?
You mentioned it earlier, I think.
The upside down triangle with the arrow over it is, here, that was perfect. This is the gradient
Yes. That's what
operator. This symbol, when you're using like LaTeX, is nabla. Why? I have no idea. Just a curiosity in case you find, okay, I said using LaTeX. Microsoft Word now, its equation editor, you can use LaTeX commands for a lot of things. So if you're trying to make an equation and put that in, you can put like /nabla to get the upside down triangle. And this is backward from how you would do it in LaTeX actually. Go away.
Is that Word or Excel?
Either one. I'm not sure how equations are used in Excel offhand. I'm not sure why that 100%, 108% thing is popping up on. This is how you would put it in. /nabla/vec.
It's a forward slash, backward slash.
Whatever direction that slash is. I can never decide if it's forward or backward because it just depends on how you look at it.
Oh, that didn't happen.
Yeah, are you an equation editor in one of the Word or one of the Office suites?
No, I'm just in Word.
Yeah, you have to be an equation editor. Okay. Anyway, that was unimportant.
Yes.
Just a curiosity in case you like are writing a paper and you need to.
Right.
Okay, so
what's that bottom equation then?
this equation here.
Yeah.
That's the equation to go from having the electric potential to find the electric field. That's actually really significantly useful because electric potential is a scalar. So if I have let's say 2 point charges, I find the electric potential due to those 2 point charges, add them together as scalars. Really easy to add, just 2 numbers, right? Well, 2 functions. And then if I take minus the gradient of that function, it will give me the electric field vector. So I can get not just the electric magnitude, but also its direction from the scalar electric potential. So we like to work with electric potentials as we work through problems. And then at the end, when we're looking for force, well, then we do this, we get the electric field, then we charge multiply by Q, and we get the force. Now, I want to do some examples with this because you haven't done any examples with this equation. You probably haven't seen that until today. So, a point charge. V is equal to KQ over R for a point charge. That has built in a reference point. The built-in reference point is if you're at infinite distance from the charge, V is 0. Because remember, the definition of V is always by delta V. Right. It's always in reference to some location, and our reference point here is V at R equals infinity is 0. The gradient operator in spherical coordinates, notice that's VQ or KQ over R, so it's spherical coordinates. The gradient operator in spherical coordinates is shown there. So what's the electric field do to a point charge? You already know the answer. We've done that too many ways to count. Do the math based on that equation. Yeah, the electric field of a point charge is KQ over R squared. And the direction is out of positive into negative.
Right.
So we want to see if that's what we get.
Okay.
So do the work. You do it.
Where do I start?
So
that's my voltage. That's going to be delta V.
start right here. You can make it flat or whatever if you want.
That's fine.
And just scroll up to get your. I have a blank slide there for you to work.
No, I'm just straight up confused on how to start this problem.
Okay.
That's what I'm confused
Not the
about.
question I was answering.
No.
Okay, so
Because
our definition is that box.
Right. And so this is my gradient.
Uh-huh.
And this is my V.
Right.
And I'm looking for the electric field. So basically I take I take my gradient, negative the gradient, and multiply it by this V.
Operates on, but yes, that's just terminology.
Operates on?
Yeah.
What does that even mean?
We call it an operator because it does a mathematical function on another function.
Okay, so basically I would be writing this out as, scroll up a little bit, r hat partial derivative of r plus 1 over r it doesn't work.
No,
that
it
way.
works.
It does? Oh, there we go. And then,
It's just speed.
There. That. Hat. What is that?
Partial derivative.
No, this.
Oh, phi.
Phi.
Phi, phi, pho, fum. A lot of people say phi. I learned to say phi because that's what my Greek classmate called it.
Sine of phi. Theta hat. Partial derivative of theta. And so I take that.
Parenthesis around that whole thing.
Around that whole thing and multiply it by the K over KQR.
And then there's one more thing, my sign out front.
Right, because it's the negative gradient.
Yep.
Okay. So then let's see. I don't remember how to do partial derivatives.
Partial derivative means that anything that's not that variable is a constant.
So then this is a constant.
Well, this is acting on KQ over R.
Okay. Oh, so all of this is acting on KQ over R.
So for the first term, okay, so you can put minus R hat first. And then it's partial derivative with respect to R of KQ over R. So that means that theta and phi are constant.
Right.
So if you're taking with respect to R and theta and phi are constant, what's the derivative with respect to R of KQ over R?
Gotta do my division thing. Right? No.
It's R to the minus 1.
Yeah, R to the minus 1. So that's going to be KQ R to the minus 1. And then I subtract from that, multiply by the new one. So that's going to be KQ negative 2 R to the minus 2.
If you bring down the original. So that's going to be minus 1, not minus 2. Integral, it's the new one. Derivative is the old one.
That's right. So negative R to the minus 2.
Yeah.
So
make sure you put parentheses around the negative R to the minus 2 or else it looks like you're subtracting. Okay, so that's what you have right here.
KQ over R squared, and that's negative.
So put here parenthesis minus KQ over R squared. Okay, then we have minus 1 over R phi hat partial with respect to phi of KQ over R.
Which there isn't any, so that's a constant.
And so what's the derivative of constant?
0.
Okay. Okay.
Plus.
Well, minus because of the leading minus. Not that it matters because
It's going to go to 0.
Yeah.
1 over R sine phi. Okay, so why is there a phi there?
It's just what it is. I mean, you can read up on the derivation of the gradient operator in spherical coordinates, but for our purposes.
And that's times a constant. I'm going to erase this because it's in the way. Times 0.
Actually, it's the whole derivative is 0. It's not the derivative of 0. That's the derivative of the constant. Really is. Okay, so what do we have then for our answer?
That goes to 0. That goes to 0. So then what we have for the answer, KQ Q over R squared in the R hat direction.
Okay, so we have the electric field vector. And that's exactly what we knew it was going to be. It's in the R hat is the vector pointing away from the charge.
Mm-hmm.
And so it's away if Q is positive, it's in if Q is negative.
That's right.
Okay, now I got another problem for you.
Okay.
You had, does that
We
look
have
familiar?
this, yes.
I want to do both directions now. Now this here is in Cartesian coordinates.
Mm-hmm.
So do you know what gradient is in Cartesian coordinates? I'm not sure if I wrote it down. No, I didn't.
No, I don't.
Okay. It's really simple, which is good, right?
Yes.
Simple is always good. So in Cartesian coordinates, the gradient operator is equal to x hat d dx plus y hat d dy
Plus Z hat D DZ.
Yeah. Okay. So that makes life a little easy.
Considerably. Okay. So then, once again, we just take.
Oh, and what is dx vector? It's not written down.
Oh.
It's just going to be x hat d dx plus y hat d dy plus c hat d.
So dx vector is equal to
X hat d dx.
the same thing.
No, x hat d dx.
Oh.
Or excuse me, I was saying it wrong. It's x hat dx
It's x hat dx. That's all. Okay.
plus y hat dy plus c hat dz.
X hat dx.
Yeah. Plus y hat dy plus c hat dz.
Okay. So that's what that is.
So now we can do the work.
Right. So for the work, we just do the same thing we did last time. So we do, let's see, open x hat.
Well, first thing we need to do is find the voltage because, sorry, I'm trying to do this while you're right. Okay. We have the electric field, so we're going to try to find the voltage, and then from the voltage, we're going to make sure that we come back to the electric field. So the first thing you're doing is that integral. Delta V is equal to.
Okay, so negative integral of negative e sub 0 times a e to the negative alpha z plus b e negative beta z z hat direction times
Dot.
and then that
Thing. Yeah.
x hat dx plus y hat dy plus c hat dz.
Make sure you put parentheses around. Okay. How's life get easy? What is the dot product?
Parallel.
Parallel. So what direction is your electric field?
It's out? No.
Look at your equation.
It's
What carries the direction in that equation?
this negative sign.
Mm-hmm.
No?
The direction.
Z hat.
So what part of your dx is in the z hat direction?
This one.
Okay, so since this is only one direction,
Right.
this simplifies, right? Just like all the dot products we've been doing in Gauss's
Mhm.
law. So how can we rewrite this as a simpler form? Remember, we had like integral of E dot dA is equal to integral of E times dA if they were parallel, right?
Right.
And it's equal to 0 if they're perpendicular.
Mm-hmm. So these ones are 0.
Yes.
So, but we can't just get rid of them.
Yes, we can.
Oh.
Because they're perpendicular, when we do the dot product, they're zeros. And then z hat dot z hat is, remember, z hat means it's a unit vector in the z direction.
Right.
And so when you do the dot product, z hat dot z hat's just 1 because it's 1 times 1.
So
and
then
you drop the
this just goes down to
Well, minus and minus is a plus. You can drop those two minus signs.
a e negative alpha z plus b not beta.
That's okay. I made that mistake. Remember?
E negative beta z dz.
Right. So now you got to do that integral.
Okay, and this integral is going to be, do I really care about things? We're going from 0 to infinity, aren't we?
We're going to go from 0 to, let's say, h, where h is our elevation.
Okay. So brackets open.
So that's the voltage difference between the surface of the Earth and whatever elevation we're at.
Right. So E sub 0 because that's a constant.
Mm-hmm.
Then it's going to be negative alpha A e to the negative.
Integral you divide. That's fine. Oh, you're going to move stuff over?
I am. It
Okay.
irks me.
I can respect that. Next term.
Okay. That's from 0 to h.
All right.
And that is delta V, but I gotta probably. Is there another sheet down there?
There is. We'll throw in a blank
We'll throw
sheet.
in a blank sheet because we will need one.
So, come on. This button, manipulation. See what it says manipulation.
Page down there it is. Insert.
Yeah, let's put two just to be safe.
Okay.
And they should be, yep, there they are.
Okay. So then from here we plug in H and then 0 for
Right.
our Z's.
Right.
So it equals E sub 0 times negative E negative H alpha over alpha minus B E negative H beta over beta minus, except it's going to be plus because of that sign, alpha E negative alpha times 0 alpha plus, yeah, B E negative beta times 0 over beta.
Bueno. No.
That doesn't?
E to the 0 is 1. Okay, that's. Okay, that was quick.
E to the 0 is 1?
Yeah.
That's right. Anything raised to 0 is 1, not 0. So then that's just going to go to...
So now let's just be simple about this. There's no H in this, right?
Right.
So this here is going to be our reference V0.
Why?
Because we have a reference position.
Oh, okay.
Our reference position was at 0 here.
Mm-hmm.
And so it's a constant. We could have used a different reference. We could have gone from H1 to H2, right?
Yeah.
And then we're going to rewrite this. Okay, so we had H. So H is our variable instead of Z.
Right.
So I'm going to actually write this down because I'm just, so we have delta V is equal to minus E0 times A over alpha e to the minus alpha. And I'm rewriting Z now
Okay.
because H was whatever elevation is and Z was our elevation, right?
Right.
We just didn't have Z because that was variable of integration.
Plus B over beta E negative beta Z plus V sub 0.
Okay, so there we have it.
That's delta V.
Yeah.
So now we take that and multiply it by, what are we looking for again?
So, well, I'm going to do one more thing.
Okay.
Since that's delta V, then I'm going to say my V alone is this term here. Well, I'll just do it this way. This here is my V.
That
Delta
makes
V
sense.
is V, and this
V-
actually should have been minus V0.
Except why do I have this plus there?
Because this has minus as well. Minus and minus made the plus.
Yes, that makes sense.
Okay, so this here was minus V0.
Right.
So now that we have that, now we want to reverse and see if we get back to the right electric field.
Mm-hmm.
So if we have V is equal to minus E0, well, I don't know why I'm writing it down, but I could have just copied and pasted.
Yeah.
So if that's V, now
Right.
we want to find what the electric field is.
And so now we just multiply this by our
Change the
gradient. Right?
So it's minus the gradient.
Yep, minus the gradient times that. Okay. So yes, okay. Okay, so we've got the negative of x hat dx ddx plus y hat d dy plus z hat d dz times. I'm going to change things a little bit. This is a negative, and my
You're taking the negative side out. Okay.
A alpha d negative alpha z d over beta e to the negative beta z. Okay, so there's that. And I am taking the derivative of this with respect to x.
So let's talk through the derivatives first. What's the partial with respect to x of this stuff?
There is no x in there,
Correct.
so it should be 0.
Correct. What's the partial with respect to y of this stuff?
Also 0 because there is no y.
What's the partial with respect to z of this stuff?
It's the reverse of the integral.
Okay, so, well, let's just stick here.
Okay.
It is the reverse. We're going to bring down a minus alpha for this term and bring down a minus beta.
Mm-hmm.
So what's that going to do? Bring down a minus beta. It's going to change it to negative.
Change it to negative,
And
and
the
then
beta
the base
cancels.
cancels out.
Bring down the minus alpha. Change the negative. The
Mhm.
alpha's canceled.
Right.
So we can do this. We don't have to do all of the work in between because it's something we can do in our head.
Right. So that equals e sub 0 times. I'm going to write out my work just so I don't get confused. Not plus. Minus. Beta. E over beta. E beta z. Those two cancel out. Those two
There's
cancel.
one more thing you forgot. Z hat. It's a vector.
It's a vector. Right.
Okay, and there's our answer. Is that what we had before? It's got a negative out front because you had a negative in both terms.
It is.
E0. Yeah. So what we've done here is we just made sure that the math really does reverse because we said it should. We said that's what they did, but
Mm-hmm.
it's a lot more convincing when you actually work it through and say, ah, yes, that really was a reverse operation. Okay. Understand?
It's more understandable now. Yes.
More understand. It was all new. Yeah. Okay. Last thing, and we will pick up on this next week, which means that it won't be on the test next week. If this is on a test, it'll be on the test after this, for good reason. Because transient circuits could be a capacitor or inductor until the next. So this is new material. You remember a capacitor. What is the design for capacitors we talked about in class? The only design we talked about in class. Symbol was like this for a capacitor, right?
Yes, 2 equal 1. Yeah. That's because that's how we design a simple capacitor. Two parallel plates. And the capacitance has the physical capacitance, if it's two parallel plates, of C equals kappa epsilon 0 area over separation. So capacitance, it has a value based on your construction if you have a parallel plate capacitor. No charge should pass between the plates because there's a gap. No circuit, in other words. But what does a capacitor do? Stores energy in the form of charge separation.
Charge separation.
Because one plate will be plus Q, one plate will be minus Q. And that sets up an electric field, so you can also say it stores it in the form of electric field. Well, we have the relationship for capacitor. This was the physical capacitance, but the definition of capacitance was the charge divided by the voltage difference. So given that relationship, I can solve this for Q is equal to VC. And if I just take the derivative of both sides, I'm going to take the uppercase Q and convert it to a lowercase q, uppercase C and convert it to a lowercase v, and I'm going to put subscript C. The reason for that is uppercase in theory means doesn't move. Lowercase in theory it's moving or can change. So, right, voltage to change the charge. So if I take that equation and I take the derivative of both sides with respect to time, so just shifting between lines, d dt, the capacitance is a physical construct. It's not changing with time, so it's a constant. So that's just equal to dq dt on the left side equals c dvc dt on the right side. But the definition of dq dt is current. So we have a relationship between current and a capacitor and the rate at which the voltage across the capacitor is changing. Okay. And that was really straightforward. Question.
How did you get from the capital Q, V, C to the other thing again?
To the lowercase? Yeah. I was just changing the symbols because lowercase means it can change.
Okay. So it's just
nothing happened. Nothing happened at all.
It's just okay. And then you took the derivative with respect to time.
Yep.
Okay.
So this here is a fundamental relation that talks about the rate at which current is flowing. C is constant because that's the capacitance.
Okay.
And the capacitance is based on physical parameters.
Okay.
But the key here is current into or out of a capacitor. Not current through a capacitor because you should have no charge going between the plates.
Right.
But what you're doing is you're having more charge on one plate and less charge on the other. You're charging it up. So the charge is coming in on one side, so current's flowing in. Charge is leaving on the other side, current's flowing out. And of course, my in and outs are predicated on the physical positive charge carriers.
Right.
And so the rate at which it's charging, I, right, dq dt, that's the rate at which it's charging, is c dv dt. This is a really important relationship. And for today, we're going to end with just analyzing what this calculus equation means. So, what can you tell me about the limits on current? Can current be positive?
Yes.
Yes. Can current be zero?
Yes.
Can current be negative?
Meaning it's going in the reverse direction.
Yeah.
Yes.
Can current be infinite?
Theoretically, yes. It can't.
You would have to have an infinite amount of charge moving each second. That's not physical.
That's not physical. Yeah. That's not possible.
So current cannot be infinite.
Right.
Well, look at the right side. Obviously, capacitance, assuming that your plates aren't touching each other, the capacitance is not going to be infinite. So that means we can't have dV dt be infinite.
Yes. That makes sense.
That means if dV dt is not infinite, that means you have a slope that's finite. It could be from here to here, but it can't be vertical. Translation, no discontinuous jumps in voltage. You'd have to have an infinite slope for the voltage to jump from like 0 volts to 5 volts.
Right.
So that can't happen on a capacitor. It has to be smooth. It has to take some time. I say smooth. It doesn't have to be smooth. It has to be continuous.
Right.
It has to take some time to change voltage. So that's an important outcome of this. A capacitor's voltage cannot jump. It has to be a continuous function. It can have a sharp change in angle, but it can't jump. And so that's going to give us an important evaluation tool for a transient circuit. A transient circuit is a circuit where we have connected this way before time equals 0, and this way after time equals 0. We flip a switch. But the voltage on the capacitor can't change when I flip that switch. It has to stay the same.
So basically, you're saying that the voltage has to be constant throughout this entire process.
It has to be continuous. It can't change in the instant I flip the switch.
Oh,
It can be changing before, it can be changing after.
Right.
But it has to be the same value at the time I flip the switch. It can't go like this.
Ah.
So that's going to be an important thing when we evaluate transients, which I will talk about in lecture next week because we're ready for the test now. What are you going to have in the test? You're going to have next week, yeah. Not today. What you're going to have on the test is something that has one of these equations here, or, and of course, all the stuff between there and the next thing I'm stopping at is using those, or this.
Okay.
That's what you're going to have calculus-based. Something that has to do with those.
Mm-hmm.
Any questions, my friend?
Can't think of any.
All right, then I will stop the recording, and then I'm going to look at the lab guide so I can answer your question.